Hello, in this video we're going to have a look at simultaneous linear equations. So in the previous video we saw that linear equations can have two variables in them, and this is an example of one here, y equals 2x plus 1. So we can express this in table format to show that there are in fact infinite number of solutions, and by solution we simply mean that for a given value of x there is a given value of y, and this occurs over and over and over again. So there are multiple solutions, to be more precise, infinite. In the case of this one. So for example, when x equals 0, y would equal 2 times 0, which is 0, plus 1, which is 1. When x equals 1, you'd have 2 times 1, which is 2, plus 1, which equals 3. When x equals 2, you'd have y equal to 5, and so on. Similarly, for y equals 3x plus 2, we would have 3 times 0 is 0, plus 2 is 2. We would then have 3 times 1 is 3, plus 2 is 5. And then we would have 3 times 2 is 6, plus 2 is 8, and so on. So there's an infinite number of solutions. And this is a solution pair, often written as coordinates. So we've got 0, 1, 1, 3, 2, 5, etc. All of these satisfy the equation. And that means that if I substitute this into for x and calculate it, I get the y value. So what does this all mean? If I graphed both of these equations on the one set of axes, we would see that the graph represents all possible solutions, whole number or not. So that includes fractions, decimals, and so on. This would be y equals 2x plus 1, and this would be y equals 3x plus 2. And we can see that's cutting through at 2, and this is cutting through the y-axis at 1. We can also see that there is a unique point down here somewhere where the lines cross over. And that means at that point there, the x coordinate and the y coordinate satisfy both equations. I've written this down here next so you can sort of see it. So when we're asked to solve a set of simultaneous equations, this is what it means. We want to find the unique pair of values that satisfies both equations, and graphically we call that the point of intersection. So this is called the point of intersection. Okay, it's the one solution, the one pair of x, y values that both satisfies the red one and the blue one. Okay, let's get into it with an example. So we're down on slide 4 now. So we've got y equals 2x plus 1 and y equals 3x plus 2. And we're going to use the substitution method. And the substitution method simply says that if I can express one variable in terms of the other variable, then I can utilize that in the second equation. So I'm going to label this one as equation 1, and I'll label this one as equation 2. And I'm going to substitute 2x plus 1 for y in equation 2. So can you see that because I'm saying that 2x plus 1 is the same as y, and because I need to find the simultaneous solution, then I can simply replace y here with this expression here. So that gives me 2x plus 1 instead of the y is equal to 3x plus 2. Now we have an equation with a single unknown which we can then solve. So our usual methods of solving apply. I eliminate the variable from one side of the equation, easier to do it and keep x positive. So I'm subtracting 2x from both sides to get 1 is equal to x plus 2. And then I eliminate whatever else I need to get x by itself. In this case, it's fairly easy. I just subtract 2 from both sides to get negative 1 is equal to x. Okay, or x equals negative 1. Now again, I'm cramping for room here. This is not a full solution yet, it's just the x coordinate. So now I go back to the other equation. It's good practice just to go to the other equation and substitute in. So now I'm going to substitute negative 1 for x in equation 1. Like so. So I'll have y is equal to 2 multiplied by negative 1. That's just how I do my notation for multiplication. Plus 1. 2 times negative 1. You could do this in your head, obviously, but 2 times negative 1 is negative 2 plus 1, which is also equal to negative 1. Therefore, the solution is xy, we normally put x first, is equal to -1, -1. Okay, hope that makes sense. Let's have a look at one more example. Now, in this example here, we don't have y equals something and y equals something. But of course, we can manipulate that until it does. So we can say in 1, y is equal to 3x plus 4. Can you see what I did there? I just added 4 to both sides to get rid of the -4. Now I'm going to substitute into 2. So instead of y, I'm going to write 3x plus 4. So this y here is now replaced with 3x plus 4. And then I'm going to write the rest of it out. Minus 5x plus 6 is equal to 0. I'm now going to simplify this left-hand side. 3x take 5x is -2x. And plus 4 plus 6 is equal to plus 10 is equal to 0. I'm now going to add 2x to both sides just because I like to keep x's positive when I can. So I've got 10 is equal to 2x. I'm not going to be phased with the fact that the variable's on the right-hand side. And then I'm going to divide both sides by 5 to get x is equal to 2. I've just flipped them over again because we can be flexible with our thinking there. It doesn't matter which side x is as long as we flip the entire of both sides. So I've got x equals 2, but as I said last time, our job is not done yet. So I used equation 2 then, so I'll go back to equation 1. So substitute x equals 2 is another way of writing it. Substitute x equals 2 in equation 1. And so I have y minus 4 is equal to 3 multiplied by 2. Notice I used the original form of that equation, not the manipulated one. And now I'll just simplify and solve. 3 2s are 6. Add 4 to both sides to get y is equal to 10. Therefore, xy is equal to 2, 10. That is the point of intersection. That is the point which is a solution for this equation as well as for this equation. Now, what I haven't done, but what you can do, and it's good practice to do if you can, is if I take 2, 10 and substitute in for x and y here, I should get 0 from that substitution. In other words, that equation should work as well. So it's always handy to check in the other equation if you have time. So if time permits. Okay, so just keep that in mind. Okay, that's it. So have a go at doing some of the problems yourself using the substitution method. And in the next video, we'll go through yet another method.